My name is Ram Sagar. I am working presently at Indian Institute of Astrophysics, Bangalore as a retired scientist, NASI Senior Scientist Platinum Jubilee Fellow. In this talk, I am going to explain various processes of star formation in a galaxy. Before really starting this aspect, let me explain you a very important diagram in astrophysics, what we called Hertzsprung-Russell diagram, or in brief HR diagram. It is a luminosity temperature diagram. So, if you see on x axis, this is spectral type of stars, from hot stars O to low temperature stars M. On the upper side of the same axis, if you see, the temperatures are denoted. On y axis, on this side it is luminosity, and equivalent to that, what we use a unit in astronomy, absolute magnitude, that is shown here. And if you see the star's mass range, we measure in terms of the mass of sun, and one sun mass is 2 into 10 power 33 grams, and luminosity of stars are also measured in unit of luminosity of sun, taking as a unity. So, you can see L sun is equal to 4 into 10 power 33 ergs. So, whatever we are measuring here, this is log of luminosity, and unity is this. So, the mass range in the stars, it is 0.1 to 120 solar mass, and in fact, luminosity and mass, they are related by this relation, that is luminosity is directly proportional to the about 3.8 power of mass. So, these properties, they are based on observations. One more thing which we can see, that in the diagram we have a long, very large number of stars, they occupy this portion of the HR diagram, and this is called main sequence star. In other words, that is where the hydrogen burning starts in the nucleus. So, during this phase, when all the stars were on the main sequence, main source of energy is hydrogen at the nucleus. Then we have giants, they are the phases of the stars, which are, as you can see, moving towards lower temperature, and then we have supergiants. So, between these two type of star, main difference is the mass. They are relatively lower mass, they are relatively higher mass. Then we have white dwarf, which is the end stage of the stars. So, one can see, these are the regions which I will try to explain in the lectures later on, why maximum number of stars are on the main sequence. The reason is, in the star lifetime of a star, maximum time hydrogen burning takes place, and that is why you find maximum number of stars in this part of the diagram. Now, this slide I am taking help of modern observational proof for star formation processes, which we have learned during last few decades. It is with the help of Hubble Space Telescope, HST, ALMA, and infrared sources, and also people have developed theoretical expertise using computing power, in other words numerical simulation. So, these two development, that is modern observational and theoretical developments, they have significantly improved our knowledge of process that governs formation and evolution of stars. Despite these developments, we have few, I will say, frontline research problem is still not understood. One of them is, that is, do not have a predictive theory of star formation, that exactly what are the boundary condition and how things form. We roughly know. Other parameter which is very important, which we do not know exactly, it is a star formation efficiency. In fact, this is defined as the fraction of the molecular cloud from which stars are formed, which is converted into stars. How it happens, what is the exact number, and factors which governs it, they are not well known. Third is initial mass function. For example, at the time of the star formation, what is the relative frequency of masses of the stars, which we called initial mass function. They are not clearly understood, and their dependence on the star formation processes are least understood even today. Other observational fact which I would like to highlight here, that probability of a single star formation is very remote. In fact, I will explain in the next slide that how this process takes place. Then whatever molecular cloud exists in our galaxy are known. We have not physical conditions that can produce a single star alone. In reality, we always group of stars are formed and which are called star clusters. Now, another fact which has been established based on these observational and numerical simulation, that once a star is formed and nuclear burning starts at the center, all uncertain details of star formation processes are no longer relevant to its further evolution. In fact, further hydrogen burning, then to helium burning, and further evolution, its late stages, they do not depend upon the initial conditions of these star formation. Now, in this diagram, I am just showing you that a picture which is of M16. It is a huge molecular cloud. That is where stars are formed, and you can see very clearly what a beautiful picture taken with HST with higher angular resolution. So, that finer details of the molecular cloud, these are known, and you can see there is a contrast, well defined boundary, and there are newly born stars, they are also visible. So, this is star forming regions, and this is one example, but in fact, in our galaxy there are several such star forming regions like Horsehead Nebula and Carina regions, Orion regions. In all these regions, stars are presently in the process of formation. Next slide, I am trying to explain briefly about the star formation and what is observational support for this. In fact, giant molecular cloud, why we are saying, because the mass of this cloud which are observed in our galaxy, it ranges from 10 to the power 4 to 10 power 6 solar mass. So, it is a huge mass spread over a large area, and in fact, hydrogen is prominent, diffuse hydrogen, and typical temperature in such molecular clouds, it is about 100 degree Kelvin, and density of the hydrogen is not very large, it is a 10 power 7 atom per cubic centimeter, in this type of cloud, we can say that they are floating in the space, just like a thermodynamics we study in physics. In that process, interesting things happen, and that is what is mentioned in the next slide. I will just briefly explain and then go back to the earlier slide. What are the important phases of star formation? If suppose this stable molecular cloud, giant molecular cloud, it gets perturbed by some physical processes like density wave or supernova explosions, then free fall of the colex starts, and through fluid dynamics, Jeans was the first to provide this Jeans instability strip concept and process of gravitational collapse, which if I go back to the earlier slide, you will see that this is at this temperature, at this Jeans mass is 30,000 solar mass. So, it means under these physical conditions, this cloud, if its mass is more than 30,000 solar mass, then it will start collapsing, and when it collapses, then it fragments, it becomes into smaller parts. The reason is, as you can see, gene mass depends on density as well as the temperature of the cloud, which is given below, and whenever Jeans mass is there, then this fragments. So, it becomes in two parts, and then these two clouds, they collapse independently. Again the same principle applies, and it breaks into pieces, further fragmentation take place, and finally, a group of stars they appear. And in fact, this equation tells us that how Jeans mass depends upon density and temperature of the cloud. And in this process, dense core of a giant molecular cloud, if you see, then the temperature it has become cold, because during the gravitational process cloud was still optically thick. So, the whatever gravitational contraction took place, that energy is radiated away, it has cooled, but density of the cloud it has increased. As a result, this dependence of the Jeans mass indicate that now for low temperature and high density dense core molecular cloud, Jeans mass has reduced now to 7.5 solar mass, which was earlier for a diffuse hydrogen cloud of temperature 100 degree Kelvin and density 10 power 7 cubic meter, it was 30,000 solar mass. In this, interesting thing is that finally each star becomes independent, but and the entire process, it's not, it takes few years, but it takes few mega years, 1 to 10 mega years, and end product is a star cluster. Things which are still not understood, duration of star formation, how long it happen, which stars form first, massive or low mass, and initial mass function, that initially what is the relative frequency of mass distribution of stars, and these in fact are the burning or frontline astrophysical questions which present day researchers are interested in handling them. So, this aspect I just explained you, that the important phases of star formation can be summarized in this, that is the initial free fall collapse of the present parent molecular cloud, which I called giant molecular cloud, and it is governed basically by gene instability and gravitational collapse. Then cloud fragmentation leading to a range of stellar masses, and finally, we have formation of a protostellar core. That is, this is the stage. Before this, star cannot be located or put into HR diagram, which I explained right in the beginning. At this stage, star appears first time on the Hertzsprung-Russell diagram, and that is what we call pre-main sequence phase. And once it appears to this stage, its further evolution is not dependent on the process of star formation, and also not depending much upon other physical conditions of the star. In fact, star formation is considered to be complete once the star appear on the zero age mean sequence and hydrogen burning in the nucleus of star starts. And in fact, that is why we observed in the very first slide that zero age mean sequence, they are relatively very large in number. In fact, about 80 to 85% of the stars observed on the main sequence. It is simply because of the fact that hydrogen burning in the nucleus of the star, it takes maximum time. This slide in fact is describing initial mass function based on the recent studies. Here x axis denotes mass from larger mass to smaller mass. This is on logarithmic scale. So, 0 means 1 solar mass, and these are higher mass, these are subsolar mass. So, if we call what we call slope of the function, which is larger than 1 solar mass, we called this thing Salpeter mass function, and in fact, mass larger than 0.6 solar mass, they have minus 1.35 slope. If we go to lower mass, then they have different slope, still negative, it is minus 2. But if we take subsolar mass star in this range, then the slope changes and it becomes plus 1. So, this is HR diagram where protostar appears first time, and in this part of the diagram you will see this is the location, and this is just showing a sketch diagram that what are the physical processes which are involved, and this physical track was first done by Hayashi, and that is why it is also called Hayashi track. In fact, this is also known as Hayashi forbidden region. So, this part star will not appear, and then it is it's a while it is moving from here to here, it's a star fully convective during this process. And in this Hayashi track, because of the lower density in the outer star, relatively lower density, it is fully convective. So, the radiation process is convective, and as soon as it reaches to this point, then during this phase the core becomes, now it develops radiative core. This is the place where radiative core develops, and then following this process it finally reaches to the zero age main sequence. So, in this process the temperature and pressure in the core, it becomes high enough to ignite nuclear reaction in the star, and when it reaches here, we call it hydrogen burning or hydrogen fusion. It starts, and this is called main sequence or zero age main sequence star. So, this is the typical process through which a pre main sequence phase goes through, and how long this phase take, it depends upon the mass of the star, which is displayed on the other side of the diagram. Here again we have x axis as a spectral type and y axis as a luminosity, and this is the location of zero age main sequence stars, and this star is of 0.5 solar mass, and time taken by this star is 150 million year, while a solar mass star, it takes 50 million year. If we go to the higher mass star, which is 3 solar mass, 9 solar mass and 15 solar mass, they take 3 million year, 1.5 million year and 0.6 million year respectively. So, from this we see very clearly that the pre-main sequence phase lifetime of low mass star is very large. As mass increases, their pre-main sequence phase lifetime decreases, and massive stars, they end up at a higher temperature, where hydrogen burning stars like O type of stars, they have masses more than 15 solar mass or so, and then we have other spectral type which are in between, and 1 solar mass means it is about G type and subsolar mass. And if in this process of pre-main sequence phase, if a star is unable to ignite hydrogen burning at the center, then we do not call it a star. In fact, by definition, stars are which are self shining, and the source of shine, source of energy has to be nuclear fusion. So, as per theoretical models, the lowest mass stars, depending upon various physical conditions, it is around 0.08 solar mass. If we have a pre-main sequence, stage where mass is less than 0.0806 solar mass, it will not end up as a main sequence star. In other words, hydrogen burning will not start in those stars. Thank you.